Open the second window. Please increase the air conditioning to maximum. Maximum air conditioning, thank you. Got that? So we're missing Nadir and Omar, of course. Unforgettable Omar. And who else? Just those two? So, where's Omar?
No idea.
Was he in earlier?
No.
Ah, okay.
Why do what teachers ask about Omar?
Because they came up on
No. No. Yes, exactly. I suppose. No, it's a fair point. He's noticed it, so I can't pretend that he's not noticed it now. Reasons. Because of reasons. Yeah. Do you? Alright. Simple circuits. Was it? Oh. So the last time I updated it must have been when I did it with January students last year then. Okay. Simple circuits.
Consistency.
Consistency?
Yeah, you're on the same lesson as you did last year. Same day, same lesson.
That's how I roll. Right. An electric circuit is a path in which electrons from a voltage or a current source flow. It must be a closed path called a circuit. In other words, it must be a loop. The point where... Now, this is what you need for the exam. The rest is just further explanation. The point where the electrons enter the circuit is called the source. The point where they leave the circuit is called the return, or the ground, earth ground. The exit point is called the return because electrons always end up at the source when they complete the path of the electrical circuit. This is what you need for the exam. What I'm trying to explain is basically this picture. The electrons leave here. This is called the source. They travel in the circuit and then they end here in the return. This is called a closed path. This is called the source, as I said. This is called the load, what actually is converting the electrical energy into work. And obviously this is called the control. So really this definition is about the basic words that we will be using in this chapter. So you do not need to write all of this. But I do want you to draw this in your notebook, please. Draw a beautiful circuit. Yeah. Give me that pad, actually. I want to see it.
Do you know how it works?
I think I'll figure it out. Which way does the batteries go in?
No batteries.
No! Come on, your teacher's not a complete idiot. This is pretty fun.
After I use this, I feel like I'm very good at drawing.
At drawing, yeah.
Which side of the battery?
This is the negative side. This is the positive.
No, I know that, but like when you draw the symbol.
Oh yeah, we haven't talked about that yet. I accidentally drew it before I actually showed you what it was. That will come up later. I'm going to give you a table of the symbols. There you go. Here's the circuit picture for you there.
The bottom one, the longer one?
No, later. But yes, it is.
Oh, okay.
Did you figure out how this works?
I'll have to think about it. So I never thought about it before.
If you do it slowly and you look how it goes, you'll understand it really quickly.
There's lots of little hexagons. So are you like pulling something up to the surface when you press down on it? It is magnets?
The pen tip is a magnet and this is
Oh, it's a magnetic ink.
no. This is
Not in.
the sand thing.
The
is not-
sand, when the
What's it
sand.
called?
So it's
Oh, there's something in it. There's something in it, powder,
Yeah.
like iron fillings or something. Yeah.
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 Those are each hexagon has an iron filling.
Ah, when you write, it pulls to the surface, and then when you run the thing across, it
There's a
it
magnet
Yes,
on
the
that
magnet.
that pulls it down.
physics.
Yeah.
Okay. have you-
Disappointed though.
No, it's amazingly, it's very similar to how e-readers work. Now, not tablets, e-readers. You know, the black and white ones.
Yeah, but I'm still disappointed.
Why? I think it's great.
No, with you, it took you a long while to.
Do you think I go home and wonder how toys work?
No, you just did it. You should have. Disappointed.
I'm sorry to disappoint you, Faisal. You will learn as you get older. Life is just one disappointment after another disappointment. It's good if you learn this lesson sooner than later. Okay, you have that? Yep. What are you doing in chemistry at the moment? Have you talked much about electrons or anything like that?
Molarity. Doing molarity.
Molarity.
Titration.
Titration. Okay, yeah. Continue. Yeah.
Is that in the middle of the diagram?
Conductors, wires. Okay. Continue? Yep, right. So now, of course, we can't draw such beautiful pictures every time we want to draw a circuit. Instead, we use some symbols that represent the parts of the circuit. Symbols you've probably seen before. This is what you were asking me a moment ago. So, this is the convention for the symbols below. This symbol represents a switch. This represents a cell, and this represents a battery. We'll talk about the difference in a moment. This represents a lamp or a light. This is the voltmeter. This is the ammeter, which measures what? Current, yeah. This is a resistor, and resistor could be anything. And this is a variable resistor. And there was one more symbol which is not on the course that I've deleted.
Diode?
No. You'll have to Google it and find the original. It can be a treasure hunt for you. So, can you please copy this in your notebook carefully, please. You are expected to know all of these for the exam, of course.
The symbol for the capacitor.
That is in a separate lesson. Yeah. We're not going to do capacitors just yet.
So we do it.
Oh, yes.
Is it for the ohm meter?
Oh, we remember we said ohm meters we don't like on this course.
What could it be?
What could it be? It's a treasure hunt. Physics Google image treasure hunt. Does anyone use Yahoo Mail?
Yeah.
Don't.
Specifically of my wife.
My account and many other people's accounts were hacked in December, and I discovered today that my account has been deleted.
wow.
Have you been using it like as you were?
No, my computer programs have been using it to send out emails. So I realised it wasn't working, so when I went to log into Yahoo Mail to see what the problem was, it said the account doesn't exist, and then there was a notice saying that there was a security breach in December.
Probably the programs you're using.
No, I don't think they deleted it because I was spamming people. I think they deleted it because the account was hacked and somebody deleted it.
You can still retrieve it.
They say the account doesn't exist. So like when I tried to recover the account, they say, we don't have this account. I said, okay, let me log in.
They just deleted you from their lives.
Yeah. They did. And it's weird because when I try to log in, it says the password's wrong. So when I say, okay, click forgotten password, I enter the email address, it says email account doesn't exist. I'm like, okay, well I'll just make the account again with the same name. So when I sign up, it says email account already exists. Why you no work? So I have a very bad impression of Yahoo now, so.
The list of things you're doing there. What should I tell them if you tell us the thing that you removed is? That's why.
Okay, do we have this drawn? There is another name for a variable resistor. A resistor who's a resistor who can have its resistance changed. I don't know if anyone knows the noun for a variable resistor. And what is it? Very good. Very good. Rheostat. Yeah. We don't really use that word on the course. The exam usually says a variable resistor. It's quite an old word, I think, rheostat. Continue?
Sir,
Yeah.
that lamp,
Yeah.
is it specific to lamps only, or is this like load, like what we saw in the other?
Yeah, good question. It is, believe it or not, specific to lamps as a light source. Loads would be represented by this symbol here.
The resistor?
Yeah, because it's offering a resistance. Yeah. Right, so let's draw the circuit we had a moment ago using these symbols. So we had this here. Then what was it connected to? A switch, wasn't it? And then connected to the... Was it a lamp or was it a load? It was a lamp.
No.
Yeah, so it's like this then.
Well, it was about.
Yeah. It's a bit complicated because there's an unfortunate use of English here. I suppose it's technically this. We'll talk about that in a moment. I guess it kind of is, should be this. Right. Series and parallel. Yeah. So.
Series are nice,
It's not. Depends on the situation. This is what we mean when we say lamps are in series, and this is what we mean when we say lamps are in parallel. Please draw these and write the words above them, series and parallel. I wasn't sure if you were asleep. Okay, did you draw this? Not yet? Yeah.
Do we have to put the dotted line between the cells and the battery?
Between the what?
Cells and the battery.
What dotted line?
Motor?
Yes. This dotted line?
No, like between, like in the symbols you gave us, the battery has like a dotted line between each cell.
I don't bother with that. No, you don't have to do that.
I hate them. This is the worst.
What is?
Logic.
Logic gate.
It's not on the course.
Yeah.
Logic gate.
It's the worst.
Continue with this? Okay, so, English time.
No.
Be strong. Okay, so, one battery is not called one battery.
Cell.
It's called a cell. Very good. Alright, do you want to tell me the next part? Two or more cells is called a battery. So, I have a 3 volt cell.
Battery.
No. This is okay. If you have a 3 volt cell, that means you have one thing that's 3 volts. I have 2 3 volt cells. Therefore, I have one very good. I have one 6 volt battery. Right. I have 3 3 volt cells. Therefore, I have one battery. Right. No, it's a 2 or more. So 3 of them can also make a battery. I have 2 batteries. No.
I have 2 cells, that is a battery.
If I have 2 batteries, I have one battery.
Yeah.
I don't have 2 batteries.
But if I have 2 cells, I have one battery.
Yeah. But if I have 2 cells here, that's called
A battery.
Battery.
2 cells here,
Battery.
battery of 4 cells. Yeah,
So you can't have more than one battery.
exactly. And this is what I mean. This is the unfortunate use of English, because in your laptop, you might say, oh yeah, or my phone, or whatever, radio, you might say, oh, it takes 6 batteries. Well, yeah, okay, it does, because what you buy in the shop is called a battery. It's just different meaning here, you know. So it's unfortunate use of English that what you call a battery in a shop is not what I'm meaning here. It's okay? Yeah. So please don't say this. I have a 3 volt cell, therefore I have one battery. This is wrong. If you have only one cell, you have only one cell. You don't have a battery. So I'm simplifying the English rules here, but it's good enough for us. Okay. Right, now, some basic rules. So we'll look at series first. Series. So, series means straight line. Let's put an ammeter here, so that's called I1. And let's put an ammeter here, we'll call that I2. And we'll say there's a current flowing through it like this. First rule. Current is constant in series. I1 equals I2. These two should have the same reading. Even if I stick something in the middle here, like a lamp, it's still I1 should equal I2. It doesn't matter. If I stick another lamp here and a resistor here, no matter, I1 equals I2 in series. First rule. Yeah? Yeah, go on.
If there were 2 cells, then it would be a battery?
No, there's no, I didn't draw in any. If you prefer, I can put the cell here.
Yeah, so if there was a cell at the start and a cell at the end, would that be called the battery?
No.
Since they're the same circuit?
No, actually, they have to be grouped together. The other thing is, the word battery in English originally meant grouping together. So you could say I think you could say like a battery of, well, it's usually a military context, so it'll be like a battery of firing soldiers or something, you know. Anyways, the only exception is if you had something weird like another cell in the middle here, then it's not true. But for simple circuits like this, it is true. Okay, next rule. Resistance is additive. So what I mean by that is you have one resistor here, one resistor here. That's the same as one resistor here of resistance R1 plus R2. So resistance adds. Or in total is R1 plus R2. So the total resistance is each one added together. They add here. Okay, write that down. So resistance is additive.
You have a minute to explain something really quick?
Yes, go ahead, Jeff.
The rule that says the current is constant
Mm.
makes sense in my head, but I want to clarify it a little bit. Now the current is flowing from A to B.
Yep.
And there's an ammeter
Yep.
over here and one
Yep.
ammeter over here.
Yeah.
The currents will be equal.
Yeah.
And this ammeter and this ammeter.
Yep. It has the same number on both ammeters, yeah.
What if something blocks the current or something disrupts it halfway before it reaches to the other ammeter?
Something like what? Give me an example. Like, are you talking about like a lamp, a resistor, or are you talking about physically cutting the wire?
No, like a resistor, yeah.
A resistor, believe it or not, does not affect the currents. So if you stick a resistor right in the middle of the two, like a big lamp or something, the current, the ammeter will give the same current on both. Because it's the voltage that gets affected, because the voltage is like the energy. And that's what the lamp is using, not the charge, not the current.
So there's no way of changing the current?
I know there is, but we'll look at that later.
So the current, not only is it the same as ammeter 1 and ammeter 2, but it doesn't change as well.
Doesn't change. Oh, you mean if you stick a resistor in the
Yeah.
middle? The current will change, but it will change on both of them.
Okay.
Yeah, so if you stick it, if you come along and stick a resistor in the middle, they'll both change together.
Yeah.
Yeah. Okay, resistance is additive. Next, voltage is different and additive. Lee, I knew you were going to fall asleep. I could see it earlier. Be strong, Lee. What time did you start at?
9.
9? Me too. Do you have coffee today? How many? At least 2, minimum. 2. 1 before lunch and 1 after lunch. Yeah. Okay, voltage is different and additive. So what I mean by that, Fuang, here we have, let's say, 1 resistor, and let's say here we have another resistor. Imagine I have a voltmeter here. It will say V1 on it. I put a voltmeter here. It will say V2 on it. V2 will not equal V. They'll be different. Okay, sometimes they can be the same if these are the same, but they're usually different. If you come along and put a voltmeter around both of them, V, what you'll find is the number here that includes both will equal the voltage around one plus the voltage around another. So the voltage is different and additive. V1 does not equal V2, but the total voltage will be V1 plus V2. So for example, if this said 3 volts and this said 2 volts, then this will have to say 5 volts. Okay, so you write that down, please.
Wow. I can draw all through here.
Please. Can't you see how tired I am? Look at me.
You always are.
Look at how tired I am.
1 more cup of coffee.
No, this is already my 4th cup today.
So I have chocolate.
Wow.
You do? This could give me the energy I need to finish the day. See, you get to go home and rest. I have to go home and do 2 more classes. Oh yeah, this is what I need.
2 more classes?
Private classes.
Oh.
Continue. Right, next. Battery. So, a plus with a minus causes an increase. But a plus and a minus, a plus with a plus or a minus with a minus causes a decrease. Let me explain that. Here is 1 cell. This is 5 volts. Here is another cell. This is 6 volts. In total, this is like 1 cell of 11 volts. This side is minus, this side is plus, this side is minus, this side is plus. However, if you put the cells in backwards like this, let's say this is 2 volts and this is 10 volts, you do not get 12 volts, instead you'll get 8 volts. So do you notice when you're putting the batteries into your toys, you always have the positive side touching the negative side, when you like stack them up. If you have one of them in backwards, you're reducing the voltage instead of increasing it. Okay, so this is the last of the series rules, then we'll look at parallel. You can write this down. So plus with a minus increases, but a plus with a plus or a minus with a minus is a decrease. Okay? Okay. Continue. Parallel. Current is different and additive. So what I mean by that is, here they are in parallel, and maybe they combine together. We actually saw this one earlier. If this current is I1 and this current is I2, then the current here on the ammeter would say I1 plus I2. And they are different. They're not equal. So you have I1 does not equal I2, but they add together. Now, maybe someone knows the deal with resistance when they're in parallel.
1.
Yeah, 1 over 1.
What's 1 over X called? You know, like, yeah, it has a name. It's called this. No, this is, a lot of people think it's called inverse, but it's not actually. This is a very, very common misuse of the word inverse. I mean, you could call it inverse, but there's another better word for it. Reciprocal, yeah. So, it's the reciprocal that's additive. 1 over R equals 1 over R1 plus 1 over R2. So what you have here is, if this is R1, and this is R2, and they're in parallel, it makes a total resistor, and you can find the total resistance by using this formula. Yeah. Right. Voltage is constant. So interesting now, if you have 2 parallel wires, the voltage should be the same in both, and the same as the total as well, which I didn't actually say, but I'll just draw it here. So imagine you have resistor here, resistor here. This one has a V1, this one has a V2. V1 must equal V2, and also, yeah, if you put a voltmeter around the total, then you'll find that that is also equal as well. So parallel voltages are the same. And finally, the battery. What happens if you put the batteries or the cells in parallel? So if you have one here, for example, and maybe one here, for example, later.
Why do you bring the idea in then?
I like the tease, you know.
What do you benefit?
Exactly, suspense. Do you know the way sometimes people put comments online that try to make someone angry, you know, trolling comments? Kind of like this.
Yeah, it's working.
Yeah, yeah.
But why is there a difference between, why is there a difference between series and parallel when it comes to current being different or constant?
What is the reason that causes them to be different, is it?
I mean, like, why is the current constant in the series but not in a parallel?
Yeah. I suppose in this lesson I'm giving you these rules as a fact, but later in this chapter we'll study something called Kirchhoff's rules, which explains... No, it's not bad. No. Kirchhoff rules are more basic rules to do with circuits, and with Kirchhoff's rules there's a reason why the rule is the way it is. So Kirchhoff has two rules, and there's an explanation for why each rule is what it is, and these rules are the reason for these rules. It's like these rules come from Kirchhoff's rules, which we'll study later. So right now, as an introduction to simple circuits, I'm just giving you these rules as facts about circuits, but it's Kirchhoff's rules. Kirchhoff is kind of like the Newton for electricity, so he has the basic rules. I used to hate Kirchhoff, but I've discovered that I now love Kirchhoff, and you will soon love Kirchhoff too.
We're still in that phase of hating.
Yeah, no, but
It's never going to change.
Fuang,
I never like.
but you like it now.
No.
You like it now.
No.
You will. Right, continuing. Let's have a look at an example. I think I will do this for you. I just want you to draw this. This cell. Oh my goodness, I said battery. What a disgrace. An absolute disgrace. This is a 5-volt cell. I'm disappointed in myself. Can you draw this with the cell in the center, please? They're going to take my physics card back off me if they see this. Come on, Faisal, draw this. What? Physics license, yeah. I'll have to redo my physics theory test. Did you draw this? Yes. Would you like to work out all the currents? Calculate the currents? Go ahead. That's what I'm going to do. Did you draw this? Mm-hmm. Okay. Can I do this one now? Yep. Okay. Let's draw this. So we have a resistor, 1 ohm, a resistor, and here a cell. And this is 1 ohm, 2 ohms, 3 ohms, and 4 ohms. This diagram is a bit complicated. We need to simplify it. I want you to use your best imagination here. This is just a wire. So I could obviously move this wire around. I don't have to keep it like this. What I'm going to do is I'm going to lift the cell up and just move it out. But I'm not going to change any of the connections. I'm still going to have it connected here and connected here. So what will happen is I'll have something like this. You know, I just pull it out from the center, just to simplify. And then what I'm going to do is I'm just going to move this so it's kind of like a diamond. Just turn it a little bit. Yes? Can you still picture this?
Just do the find that one.
No! And then I'm just going to straighten these out into a rectangle shape instead of a diamond. So I have this, and this, and this, and then this is connected here. And this is 5 volts. This one was 1, here's 1 here, isn't it? Here's 1 here. So this one is 1, this is 2. Now hang on, 4 is here, which is here, which is here, which is here. Like this. So what I've done is I've separated, so we can clearly see 1 and 2 are in series, 3 and 4 are in series, 1, 2 is in parallel with 3, 4. Okay, so this is the problem we're going to have a look at instead. So draw this and we'll start it. Yeah. Okay. You drew your circuit on your pad?
Yeah.
Let's see. Very nice. Would you like to show him?
Yeah.
This is, we'll post this on Twitter, #physics technology.
Back to basics.
Oh, we can compare writing pads. Stephen's writing pad, Fuan's writing pad. Right. So let's have a start with the current. I'll draw it in here. So here the current is, we'll say I, and here it is here, I here. But what happens here? Will the current be the same or different in parallel?
Different.
So I have to call this I2 and this one I3. They're different. Now what about the voltages? So the voltage between 1 and 2, the same or different? No, different between 1 and 2. But 1 and 2 will be the same voltage as 3 and 4. Okay. What should I do here to simplify this even more? I should add these together, shouldn't I? So what do I get on the top? 3. And what do I get on the bottom? 7. Do you see what I mean?
Yes.
And then what should I do now?
Find the IDR.
No, before that even. I simplify again using the formula 1 over R equals 1 over 3 plus 1 over 7. 2.1 is it? .1, yes, you're right. 2.1. Now, we know the R. We know the V. Using my triangle, yeah, I equals V over R, 5 over 2.1. The I is .38 amps. Now, on the original picture, be really careful. I2, or I3, which is it that I'm saying is 2.38?
On the original picture?
On this original here.
Where is the cursor?
I. This one.
Okay, yeah. I is 2.3.
Yeah, I'm saying that the I is 2.38. Okay? So now, let's look at this picture here. Let's try and get the voltage maybe next. So, what do we need if we look at the triangle to get the voltage? We'll need to know the I and the R. We know the R, yeah. But do we
don't
know
know
the?
the I
We
in
don't
this
know
one.
the. Yeah.
No, we don't.
No. So we know that this is I1, and we'll call this one here. Sorry, not I1. I should have maybe called this I1 since I called it I1, I1, I1. Okay. This is I2, and this is I3. What happens when their current is in parallel and then they come and combine together? They add. So you know I2 plus I3 should equal. Very good. Now, let's have a look here at the voltages. So you know V equals IR. So what's the voltage for this one? We'll call it V2. That's equal to I2 times R, which is 3. And the voltage for this one is I3 times 7. But what should these voltages add, or what do we know about the relationship between the voltages here? Very good, they must be equal. So you can say 3I2 must equal 7I3. Or in other words, 3I2 minus 7I3 should equal... Hey, look what I made. Look at me, I made a degree 2 system. So we can solve this. You know how to solve this from your excellent maths classes with your excellent maths teacher that you do. So I won't solve that with you. I'll just use the calculator to solve it. Mode 51, 2.38, 3 minus 7, 0. So the first answer is 1.666. No, it does. It gives me the answer for this one and then the answer for this one. And the second answer is 0.714 amps. So now we can go back to the original picture and draw these currents in. The current here between 1 and 2 is 1.667. So this one here is 1.667 amps. Between, what's the next one? Between 3 and 4 is 0.714. My arrow's not good. This is going up. And this one is going up as well. This is 0.714. Yeah, because the current is coming out here and then it's splitting. And we know the current here, what is it? It's 2.1 amps. And then here is also 2.1. So I've worked out the current in the circuit at all the different parts. Here is 2.1. What is the current here? Yeah. Here. Yeah. Here. And here. 2.1. Very good. Okay. Right. Make sure you write this one down. And I like this example because it really kind of makes use of all the rules that I've given you. So it's a good example to demonstrate how to use the rules. There is another way to do this, a better way, a way that you will learn soon.
Measuring the loops and
Using your BFF Kirchhoff.
Is it 2.1 or 2.38?
I thought I got 2.1 for the... Oh, sorry, thank you. The total is 2.38. 2.38 amps total. I was thinking of the total resistance when I got down. Who's doing electrical engineering next year?
No one.
No one?
Yeah.
What about Omar?
My dad told me not to go. He's an electrical engineer.
Mechanical.
Yeah?
As a
far away from electrical.
So different, though. Can't imagine how different it is.
It's easier, isn't it?
Easy and hard are not words I would try to use to describe different areas of engineering. I would maybe say interesting or not interesting.
Nothing. It's more interesting.
Than what?
Mechanical, that's
But
more
it depends what you find interesting.
Is it interesting for you?
Which?
Mechanical more than electrical?
Come on, of course it is. For everyone.
I don't know. I like all this logic gates electrical stuff. Sorry.
Is he gonna have to study it in mechanics?
Of course I will.
What, logic gates?
Yeah.
Maybe, it depends on the course. Okay, you got this? Yeah, okay. So, now. Huh?
the big table for the logic case.
Yes. And in fact, if anybody studies computer science, you'll probably do. Who's computer science? Are you? Computer science?
Yeah, he does more electrical than I do.
You'll do logic gates in computer science as well.
What is computer science?
The science of computers.
But what they do?
They build a computer.
Yeah,
But the science of the computers.
And
Yeah.
they make games and software and everything.
Game. Apps. Yes. Yeah, but it's a lot of programming. And there'll be a little bit of this in computer science too. Yeah. Oh, Wong is falling asleep now. I know what'll help you wake up. Some circuit questions. So if you can try these for a few minutes. And I definitely want you to finish them at home. What is the next lesson? Is it something?
We still didn't answer the question.
Which question?
The braided cables, wires. It's not here. There's nothing to do with it in this lesson.
I wonder if it's in the next lesson.
I won't fall for that again.
Hang on. Let me just have a look here. No, yeah, I thought it was, but it might be in the lesson titled Ohm's Law then.
No, I don't think it's an Ohm's law.
Alright, it is in one of the lessons later, but since I promised you the answer, I'll give it to you now. So if you have, remember in the homework we had one copper wire, and let's say the resistance in this one copper wire is R. If you have two wires braided together, and they're not insulated, so they're touching, I have no idea how to draw braided. They're braided, whatever. And this has, we worked out what is the resistance here. Is it bigger or smaller? Smaller. What would it be in total here? Or over 2, we said. Now, let's imagine we had two wires. They're braided, but they're insulated, which means they're protected. They don't touch. This is exactly the same picture as two long resistors in parallel.
So one over the...
Yeah.
Over the...
But like, if they're coming from the same source, yeah. But if they're not coming from the same
In the example I did later, I remember what it is now. It's an electrical company. So, of course, it's just sending the power down the wire from the same power plant. It's the same source.
Yeah, but like these wires.
And they're not going to the same end, so they're still separated.
Yeah, but what are you talking about?
Like wires like this.
Yeah.
Let's say two circuits were placed on top of each other.
Yeah, no, listen. It's like here. I don't have anything. When you ever look in these wires, you might see two cables wrapped around each other, but they're both protected in plastic. So it's like in the cable having two resistors in parallel. So if this has resistance of R and this has resistance of R, the total resistance is 1 over R plus 1 over R.
Is it the same way like where on the plug there are the key wires, the earth wire,
No, that's different. We'll talk about that one later. So 1 over R total is going to be 2 over R. So R total is going to be R over 2, which is the same as this one, not this one. What happens if they were...
I get you, yeah, but...
You don't like it. You're not happy. You waited the whole class and this is the answer.
No, this is like, we're saying that those two wires are staying together, then they will meet in the end.
Yeah. It depends. If they're telephone wires, you know, for talking to someone, they don't meet. If they're power cable, then they do meet.
I don't like those questions. Be clear with your questions.
But we're talking about a question which I haven't given you yet. Because you're impatient and I was trying to be a nice guy. That's the last time I'll be a nice guy to you. Right. Can you try these for a few minutes and then the next lesson...
Can we end today already? It would be really nice.
No. We still got 19 minutes left. Can you... 19. Can you try these for 9 minutes and then we'll have a 10-minute beginning of the next lesson?
Can we stop for 9 minutes and then leave 10 minutes early?
No. It's not going to kill you.
We only have one break.
She's
and
really
it was
good at
for
this.
1 hour.
Me too.
When we can both have like end our day.
It's a win-win for both.
Yeah.
Different though. I'm paid to be here.
Paid to be here.
I'll strike a deal with you. Do this for 10 full minutes starting right now, then you can go.
Okay, deal.
Deal? Now I want you working on these. I don't want you sitting there falling asleep like idiots, okay? 10 full minutes, not a second less. I'm going to take out my stopwatch as well. I'm too kind and too generous. This is my weakness. No, I don't actually, because all I'm doing by not doing the start of the next lesson is just adding the work to the next day. We haven't saved any energy by doing this.
We finished a whole lesson and we solved last lesson's questions.
I haven't started the stopwatch yet until you actually start working. I said I want 10 full hard minutes of this. Are you starting?
I started already.
No, you didn't start yet until I see something. You don't even have a pen in your hand. Are we starting? Okay, we're starting.